Hello, my dear friends. Today, in this lecture, let us solve some of the numericals on psychrometry using psychrometric chart. Me, Dr. Srikala from the Department of Mechanical Engineering, Global Academy of Technology. Now, let us take up the first numerical, which says atmospheric air having dBT of 16 degrees centigrade, that is dry bulb temperature of 16 degrees centigrade and relative humidity 25%, is passed through a furnace and then through a humidifier to maintain the final dBT of 30 degrees centigrade and 50% relative humidity. So, initially, air is at the temperature, that is dry bulb temperature of 16 degrees centigrade and relative humidity 25%, and final after heating and then humidifying, we'll get the state of the air as 30 degrees centigrade and 50% relative humidity. We need to find out the heat and the moisture added to the air during the process. So heat added during the process will be equal to mass flow rate of the air into final enthalpy minus initial enthalpy. That is the heat added to the air. Then what is the moisture added? Moisture is nothing but where the specific humidity factor comes. So moisture added will be equal to mass into omega 2 minus omega 1, that is specific humidity at the point 2 location minus specific humidity at point 1 location. Now let us first locate the points 1 and 2 on the psychrometric chart. Now let's go to the psychrometric chart. Says the point number 1 is located at 16 degrees centigrade dry bulb temperature and 25% RH. So this is 15 degrees centigrade, then this is 16 degrees centigrade. So this is the RH line of 20%, this is the RH line of 30%. So go to the middle of these two curved lines, which gives the RH of 25%. So the location with the intersection location of 16 degree dBT and 25% RH is taken as point number 1. The next is point number 2. 2 is located at 30 degree dBT. So go along the horizontal axis 30 degree dBT and go vertically till it intersects the 50% RH line. So this is the 50% RH line. It intersects 30 degree line intersects at this point. So mark that point as 2 and note down the values of H and omega at 1 and 2. At 1, so go along this line or WBT and H line normally intersects. So normally coincides. So this H1 value is obtained. So H1 value is obtained as 20, 21, 22, 23 and 23.5. So we see here H1 is 23.5 and omega 1. So go horizontally, you will find the omega 1. So omega 1 is 0.002, this is 0.0025 and 3. So in between, so it is taken as 0.0027 kg vapor per kg of the dry air. Then go to the point 2, again mark the value, find out the values of H2 and omega 2. So H2 value, how to find, go along this diagonal line. So where you find the H2 value, this is 64 and 65, so in between, so you'll get 64.5. And next, the omega 2 value, go horizontally, find the omega 2 value is 0.001325. Then how this is from 1 to 2 is how the process is achieved. So 1 to 2 is reached by two processes. One is heating process and another one is humidification process. So heating is sensible heating. Sensible heating means draw a horizontal line, the horizontal line, then from 1. Then similarly draw vertical line from 2. So that point, intersection point A. So 1 to A is the heating process. You can see here path 1 to A is the heating process. And from A to 2 is the humidification process. So during heating process, that is sensible heating, only dry bulb temperature increases. So, but the specific humidity remains constant here. But during pure humidification process, only the specific humidity value increases, maintaining the dry bulb temperature as it is. So 1 to 2 is achieved by heating from 1 to A and then humidifying from A to 2. Now based on this, we'll find the requirement, that is the required question asked is to find the heat added to the air. So heat added will be equal to mass flow rate into H2 minus H1, final enthalpy minus initial enthalpy. So it is given as H2 64.5, H1 23.5 will obtain the heat added. Similarly, moisture added will be equal to M into omega 2 minus omega 1. So substitute, we'll get the total moisture added. Since the mass is not given, it is taken as 1 kg. Next is to find the sensible heat factor. What do you mean by sensible heat factor? It is nothing but the ratio of the sensible heat to the total heat. The total heat will be nothing but the sensible heat plus the latent heat. So what is the sensible heat? Sensible heat is nothing but, since this 1 to A is the sensible heating. So what is the enthalpy added during sensible heat? HA minus H1. This is in the numerator. Denominator is the total heat. Total heat is nothing but the sensible heating from 1 to A and latent heat from A to 2. So this summation is taken as 1 to 2. So H2 minus H1 is the total heat. The sensible heat is HA minus H1. So go here, numerator HA minus H1 divided by H2 minus H1. If we write down, we'll get, if we simplify, we'll get the sensible heat factor. Next, we'll go to the next problem. The next problem, this was asked in January 2016 VTU. It is required to design an air conditioning plant for an office room with the following conditions. So here we deal with air conditioning plant. So in an air conditioning plant is located in the outdoor region of 14 degrees centigrade DBT and 10 degrees centigrade WBT. That is the outdoor condition. So what is the required indoor condition? It is 20 degrees centigrade DBT and 60% RH. So first thing we need to note down is we need to mark the points of outdoor 1 and final 2. These 2 points have to be marked. So amount of air circulation. So the air circulation per minute per person is 0.3 meter cube. So it is the seating capacity in the office is 60. So total the air conditioning office room should have the seating capacity of 60 and the amount of air per minute is 0.3. The required condition is achieved by first by heating and then by adiabatic humidifying. We should note that adiabatic humidifying. Adiabatic humidifying means the enthalpy after the heating process, the humidification process should be in such a way that the total heat Q, the enthalpy H should remain constant at the end of the humidification. So we need to determine the heating capacity of the coil as well as surface temperature if the bypass factor of the coil is given. And the next is the capacity of the humidifier. So let's see how to do this. Initially, with the given data, take the dry bulb temperature and WBT temperature, mark the points 1 and the point 2 with DBT 20 and 60% RH. So mark the point 1. So it is 14 degree DBT and 10 degree WBT. So 15 degree DBT is, and sorry, 14 degree DBT and 10 degree DBT, WBT. So how do you find the WBT? Along the DBT line 10, go vertically. The point which intersects the saturation temperature line, that point is taken as WBT 10. So from the WBT 10, so we'll draw the inclined line which touches this 14 degree DBT line and mark that point as 1. The next point should be the 2, which is 20 degree DBT. So go 20 degree DBT vertically and it should intersect at 50. This is 70. So this is 60% degree, 60% RH. So this point is 20 degree DBT and this is 60% RH. So mark the points 1 and 2. The next thing is we need to have the adiabatic humidification. So how to find the adiabatic humidification? Draw this constant enthalpy line in the reverse direction till it intersects the sensible heating line from 1. So from 1 draw horizontal line. This horizontal line should intersect the sensible heating line, that is from the 1 should intersect the constant enthalpy line from 2. So that point is marked as A. So from here 1 to A is sensible heating and A to 2 is humidification. So what type of humidification process it is? It is adiabatic humidification. That means the enthalpy should remain constant after heating during humidification. So how do you say it is humidified? So we can see that the omega value is increased from 1 to 2. That means the moisture content is added. So 1 to A, how do you say it is sensible heating? We know that during sensible heating, only the dry bulb temperature increases, whereas the specific humidity remains constant. The moisture level should remain constant. So 1 to A is sensible heating and A to 2 is humidification. So finally 1 to 2 is our requirement. So now we know that first thing is to find the heating coil capacity. So we know that heating coil capacity MA will be equal to during heating. So what is the enthalpy at the end of the heating to the enthalpy at the entry? So enthalpy at the end of the heating is A. So HA minus H1. So how do we multiply by mass flow rate? So what is the amount of air circulated? Amount of air circulated per minute MA will be equal to in the problem the volume of the air circulated per minute per person is given. So that is taken as 0.3 divided by specific volume. Specific volume is meter cube per kg. Here meter cube per minute. So meter cube get cancelled, we'll get kg per minute. So how do you get this specific volume? So at point number 1, see point number 1, so you note down the specific humidity. So this is specific humidity line of 0.8. This is specific humidity of 0.825. So this is coming near to point, so it is taken as 0.817. So 0.817 is the specific humidity. So if we substitute, we'll get the mass flow rate or the air to be circulated in kgs per minute per person. So, but for 60 persons, it is asked in the problem. So, multiply by 60, you will get it in how many kgs per minute. So, what is the heating capacity? Mass flow rate MA into HA minus H1 is the heating capacity. You will get it is in so many kilojoules per minute. So, divided by 60, if you get, you will get it as so many 4.8 kilojoules per second, or it is 4.8 kilowatts. Next is to find the surface temperature of the coil. How to find out the given data is the bypass factor. What is bypass factor? It is defined as the ratio of difference between the mean surface temperature of the coil and temperature of the air leaving the coil to the difference between the surface temperature of the coil and the temperature of the air entering the coil. So here in the numerator, it is nothing but this TdB3 is the surface coil surface temperature minus the temperature of the air leaving the coil, that is TdBA, divided by temperature of the air coil minus temperature of the air entering the coil. So see here, this is the temperature, A is the temperature of the air leaving the coil and 1 is the temperature of the air entering the heat coil. So since 1 to 2 is humidification. So the point 3, the coil temperature should always be higher than the air which is leaving the coil. So we need to find this coil temperature. So how do you find? So TdB3 minus TdBA, that means the temperature of the air leaving the coil divided by TdB3, that is coil temperature, minus TdB1, that is divided by 1 is the temperature of the air which is entering. So substitute here, we will find out the TdB3 since bypass factor is given as 0.4, and when we simplify, we'll get the coil surface temperature as 34.8 degrees centigrade. The last one is to find the capacity of the humidifier. So capacity of the humidifier means we need to go to the humidification process. Here the humidification process is from A to 2. So what is the capacity of the humidifier? It is mass flow rate m dot into omega 2 minus omega A. A is nothing but 1. Both are same. So omega 2 minus omega A. So go to mass flow rate into omega 2 minus omega A, will get the capacity of the humidifier. Now we'll go to the next problem. This is the latest problem from the video question paper. It says an air conditioning system is designed under the following condition. The outdoor condition given is 30 degree DBT and 75% RH, and the required interior condition is 22 degree centigrade DBT and 70% RH. So first thing is we need to note down these points 1 and 2, 30 degree DBT and 75% RH, and again 22 degree centigrade DBT and 70% RH. We go to the chart and see. Also it is given amount of free air circulated is given as 3.33 meter cube per second, and the coil dew point temperature. So dew point temperature of the coil is also given. So we need to note down the 3 locations. That is the inlet condition 1, required condition 2, and the dew point temperature 3. So 1, 2, 3, mark these 3 points. Then the required condition is achieved first by cooling and humidification and then by heating. So we'll see how to do that. So estimate the capacity of the cooling coil in tons of refrigeration. We need to estimate the cooling coil capacity in tons of refrigeration. And the next is capacity of the heating coil and the amount of water vapor removed. So we need to note down these 3. We need to find out or estimate these three values. So for that, first we need to we'll see the steps used. We need to note down the initial, final point and the coil DPT temperature, that is dew point temperature 1, 2 and 3 on the psychrometric chart. So we'll go to the psychrometric chart. So in this psychrometric chart, so mark the point 1. So mark point 1, it says it is 30 degree DBT. So go vertically upwards. It should intersect at 75% RH. So RH value should 75% should lie between these two. This is 70%. This is 80%. So in between. So mark that point as 1. Next, the final condition is here 20 to 20, 21, 22, 22 dBT and it is RH is 70%. So go to the 70% RH line. So 22 dBT and 70% RH line. We take this point number 2. And the third one is the dew point temperature. So dew point temperature is 14 degree DBT. So 10, 11, 12, 13 and 14. So 14, a dew point temperature means it should lie on the saturation line. So mark the intersection of 14 degree DBT with the saturated line. So mark this point as 3. Now, first the problem says it is cooling and dehumidification is the first and then the heating. So how to do that? This is the coil temperature which is that 14 degrees centigrade. So draw a line joining the point 1 and the dew point temperature, the point 3. So draw 1, 3. Then from the 2 draw, because we from that we should mark a point A in between. From there we need to go ahead with the sensible heating. Sensible heating means it should have only increase in the DBT, maintaining the specific humidity constant. So cooling and humidification, so actually it is cooling is from here to here and then from here to here. So that final cooling and humidification process is represented by 1 to 3. So draw a line 1 to 3. Then from 2, go back at the reverse direction along constant specific humidity line. That horizontal line which should intersect the line joining 1 and 3. Mark that point as A. So accordingly, now 1 to A is our cooling and humidification process and A to 2 is heating process. So totally we have reached the point 2 from A by cooling and humidification from 1 to A and A to 2 as humidification. So once we write down this, then note down the values of H and omega at each point. So point number 1, so note down the H value and the omega value. So H1 value, it is 82, omega value is 0.02. Similarly, at point location 2, note down the H2 value. H2 value is this 52.8 and the omega value is this is 0.01, this is 0.02. So in the between is 0.0115. So this is 0.0115. So this is 0.01175. So omega 2, that will be equal, note down the omega 2 value. Then note down the HA value. So HA value is 45 enthalpy, 40, this is 45, 46, 47.5 is the HA value. So note down also V1 value. V1 value is at point number 1, need to note down the V1 value. So it is 0.875, this is 0.9. So we have taken this one value as 0.882. So also note down at A, what is the dry bulb temperature? Dry bulb temperature is 15, this is 16, 16.5 is the dry bulb temperature at A. Now, First case, we need to find the capacity of the cooling coil in tons of refrigeration TOR. So cooling coil capacity will be equal to mass of the air circulated into H1 minus HA. So how do you find the mass of the free air circulated? Volume of the free air circulated divided by specific volume. So it is meter cube per second divided by meter cube per kg. It is 3.77 kg per second. Next is capacity of the cooling coil. So how do you find the capacity of the cooling coil? Mass of the air into H1 and HA, which we have noted down, that we can find out the capacity of the cooling coil. But he has asked in tons of refrigeration. So we know 1 ton of refrigeration is 3.5 kilojoules per second. So divided by that, we'll get 37.16 tons of refrigeration. The next is to find the heating coil capacity. So it is again heating coil capacity is MA into H2 minus HA. Right? So because how do you write this? Heating coil is from A to 2 is sensible heating. So it is the heating coil capacity, mass of the air into H2 minus HA is the heating coil capacity. So go heating coil capacity is H2 minus HA and substitute, will get it. Next, the amount of water vapor removed. How do you find the amount of water vapor? The humidity at the difference between the humidity at 1 minus humidity at 2. So omega 1 minus omega 2. So m into omega 1 minus omega 2 will find out the mass of the water vapor removed. Thank you.